So now we have some time for questions, of which there are many in the chat window. And let's see.
I think we did a fair job of covering everybody. So
yeah. Let's see.
Well, let's see. So there's a question from Joseph about having a high resolution structure which looks good, but the clash score is high. There is some back and forth there, but it would be good to know what some sort of general thoughts are about that. And
so it's hard for me to guess without actually seeing the structure. And it's really one of those you have to go look at it things. One of the things that can happen with high resolution structures is that there can be one region that is much less well resolved than anything else. And the refinement that deals very well with a good map can have real problems with just one loop where that's not well resolved. So it's possible that it's a very localized problem. And a structure like that can look very good on average because everything else is good except this one spot.
He's agreeing with you, the one loop problem.
Yeah, I think sometimes can be real disorder, but sometimes if alternate conformations are not modeled, that can lead to issues as well, right? And if a loop has two conformations, but it's not been modeled as two, then that can lead to distortions.
Yeah. The undowser tool might be good to look at because you can get some strange clashes out of waters, just especially at higher resolution. You can have waters that should be alternate conformations, and if they're not named alternate conformations properly, they end up, like if you have a side chain that's A and B and you just have one water there, it'll clash with both of them, but it really should be like there should be an A and a B water in two different places, and that will generate artificially high clashes. Like the water can be in the right place, it just has to be named differently, named as an alternate.
Yeah.
It's all speculation.
But it's great. There was a question, this is sort of about validation. Please educate us about the ethics of publishing structures looking at the maybe uncertainty around the ligand density. I've often seen criticism of a structures published with false ligand density. So that's a great point that there are, obviously there are many structures, ligand protein complex structures in the protein data bank where the density really doesn't support that ligand being there, or it supports a different thing being there, or it doesn't really support the interpretation that was made. So that does happen. And there are reasons. We talked about some of those things earlier on, that sometimes what actually ends up in the crystal is not what you thought it was. But of course, it's very tempting to believe it's what you want it to be, right? So I think in some cases, people have just been very optimistic about what is in there and not really applied enough of the validation metrics that we've talked about. And some of the tools, new tools like polder is one example of a tool that will help give you a clearer view of the density potentially and let you be a bit surer about what is there.
Yeah. One of the validation tools that is in the Phenix GUI but not on Molprobity, when you've completed a refinement, one of the validation tabs will actually give you some fit to map information. So you can get at some of that information there.
Yes, right. That actually is a useful thing, that if your ligand doesn't actually have a good correlation to the density, it probably suggests there is something you need to deal with. So I think this is my own personal thought, but yes, if you're doing a study where the ligand binding to the protein is the point of the study, you have to go to a lot of care to make sure that you can really justify your conclusions. I think things are a bit better these days, because in the old days there weren't validation reports for journal publications, and there weren't validation reports at the Protein Data Bank, and now there are. So often you can get a sense just from the validation report as a reviewer that there could be something not quite right. But it really is on you as a researcher to firstly convince yourself, I mean, convince yourself properly, not through bias, but through facts, that you believe what you are saying. Because in fact, it's, you know, as I said, it's tempting to want an answer, but it's not actually what the answer really is. Other questions here. Somebody asked about the RSRZ in the PDB validation reports. And this is some measure of real space fit of residues, let's say, or other things to the map. And I think somebody else, Pavel said, Pavel said this is a flawed metric. that's a strong statement. But it is true that several people have seen issues with this, where the numbers that you get would suggest a real problem, but actually the maps and the model are very clear. So it's not clear that this is a metric that we really should be using. There should be a better metric for doing things, it seems, in this RSRZ score. I don't know if you want to comment on that, Tom, because I think you've looked at this before.
No, I totally agree with what we just said, Paul. You know, it does give you a general idea if things are more different right here than they are everywhere else. So this tells you there's something different about this place, but it can put up warning flags, as you say, in cases where the density is very clear. And we just had a case where a user sent us some data where it was very, very nice data, and the RSRZ for one set of side chains was very bad, but clearly the density supported it. So it's not as you say, it's not a useful metric in general. It gives you some clues, but you can't just look at it and say, this is bad.
Yeah. So I wouldn't, I guess if you see something in a validation report that is worrying with the RSRZ, you should go and check, clearly. But if you have very clear density and the model is clear, then I think you can kind of ignore that. As Pavel says, if the correlation coefficients are very good, then that's probably a good indication that things are right. There was a question about how many waters for a high resolution structure. And Paul Emsley is in the house. Great. Hi, Paul. Paul responded by saying rule of thumb is 2 waters per residue, which, yeah, is reasonable. Then at higher resolution, you're likely to be able to see those. At lower resolution, of course, you don't see them all.
Paul also has a question about the placement of refined hydrogen atoms when determining the clash score.
So I'm worried that this is a question that I'm going to step on a landmine answering. But so
yeah, tell us what you're asking.
So historically, yeah, I see that chuckle. Historically, Molprobity has stripped out any existing hydrogens and rebuilt them, because having a consistent set of hydrogens to work with was the thing to do. It is possible that there's been a sufficient change in how people are refining and depositing hydrogens that we should now change that workflow. But the historically enforced self-consistency was a worthwhile thing to do. So that's what has been done. There is a flag, keep _ hydrogens equals true, that you can set during the clash score assessments that will not strip them out and will keep whatever you already have and assess that. So if you really want to know what is in a model as it exists, there is a way to get at that.
Great. Question from Nick about comment on adjusting the weights in refinement to improve bonds and angles. That's probably a Pavel question.
Yeah. Well, it depends. That depends what problem at hand you have. So normally you don't need to do this, and refinement should do it for you automatically. So there are only two reasons I can think of you may want to think about it. One is you observe overfitting during refinement, so the gap between R work and R3 is larger than you expect. For example, larger than what Polygon expects. So typically it's 5%, but it depends on resolution. And the other reason is you see way too many geometry outliers, geometry violations, for no obvious reason. So this is the reason to suspect that the weight between data and restraints term is not optimal. For some reason, refinement failed to find the optimal value. And yeah, that you can ask refinement to optimize that weight. So there is a keyword optimize weight, or there's a checkbox in refinement good to do so. As Nigel mentioned, it's going to be 10 times slower if you do it. It may be not if you use multiple CPUs, so it can use multiprocessing. So if you're lucky enough to have a computer with multiple CPUs, refinement allows you to specify how many processors you want to use in refinement. So ultimately, you may just not notice the runtime overhead if you have enough processors. But that's the bottom line. So normally you don't need to do it, or if you do need to do it, you must have a good reason to do it. And it may be slow, but it may be fast if you have multiple CPUs.
Yeah, and just to add to that, there is a school of thought that says the kinds of bond and angle deviations you should, has some number, some target for what that should be based on high resolution structures. And that school of thought says you should always get that kind of deviation. We're not members of that school. we don't believe that. That doesn't make sense, actually. So to be clear, you shouldn't be adjusting the weights to try to get some target value for the RMSDs. Clearly, they should make sense, but so at high resolution, those RMSDs will be higher typically, and at low resolution, they're going to be closer to zero because there's not enough information in the data to tell you what the deviations should be. Quick question about refinement. Have twin data, and I did the first round of refinement. Would it be logical to use the refined data, reflection data from that first cycle in the second refinement? So just to be clear, your data doesn't change, right? I think there may be some programs that de-twin the data when you have twin refinement. That's for making maps, right? That is not for putting back into refinement. You should never modify the reflections and read them back in as if they're the experimental data. So you always use the same data file that you start with. And we don't modify, we don't de-twin the data or anything anyway. There's a question about temperature factor variance for validation of a structure. I'm not quite sure what that means. I don't know if somebody else has an idea what that means.
It's probably the difference between B factors for bonded atoms.
Yes.
And that's the debatable, very debatable topic, how much that difference should be. I can send you back to Dale's Tronnet paper, where he classifies those differences based upon number of specific chemical environments, and those differences ranging from 2.5 to 5 or something like that. So there's a paper about it by Dale Tronnet. You can find it in that Crystallographic. I think it's section D. So, and there's a more fundamental paper on this by Hirschfeld, where it says basically states that the bond is not stretchable, so the difference should be very, very small. But in reality, as I mentioned in my presentation, the B factor is a sum of contributions arising from different motions. So we're not talking about local vibrations, talking about local vibrations plus contributions from moving in our entire chains and domains and such. So with this in mind, the variation between B factors of bonded atoms becomes less meaningful, or less interpretable, I should say. So you shouldn't take it too literally or put too much into its meaning, I should say.
There are some nice papers from Ethan Merritt as well that I think are useful, right?
Yeah, yeah.
So there's a question here about, is there anything different you need to do for the final refinement when you're ready to deposit?
Yeah, that's a very broad question.
Actually,
well, I can mention things that you should not do, right? You should not run simulated annealing, for example, for the final refinement, or you should not remove hydrogens for the last refinement run if you use them all the way through. So these are kind of things you should not do. What you should do probably, if you refine all the way with all default parameters or such, probably you want to run the final refinement with weight optimization. It's going to take more time, but it's probably going to give you a better result. But otherwise, it's really case dependent. There's no general recipe here.
I think, Nigel, you had a comment?
Right, I actually answered a slightly different way. Maybe I didn't. In the chat, I said that she had to use the output from Phenix Refine, the MMSIF, put it into the tool, model deposition tool, to add the sequence, and then that goes to one depth. I was just making sure that that is the understood process that we recommend for depositing, not to do, for instance, take the PDB file and convert that to MMSIF.
Yes.
That's an excellent point, Nigel. I just recently had a conversation about it. So yes, that's exactly what you need to do.
Yes, and for those that don't know, the protein data bank now will only take MMSIF coordinate files for crystallographic depositions, which is a good thing, actually. And there are tools in Phenix, as Nigel just described, to help set up your model file for deposition. And that will help hopefully fill more of the fields during the deposition, so there's less manual work to be done. There is still manual work, but it does actually help. And moving forward, we're going to be able to put more and more information in the CIF file to make the depositions more and more automatic, I would say, more smooth anyway. There was a question about, this is for Tom really, can you comment a bit on the Autobuild feature? I'm currently attempting to use it to rebuild flexible regions of a protein. What's the difference between the experimental map and the initial map? What map is best for rebuilding flexible regions? How do you keep the numbering correct? It seems that Autobuild changes the numbering.
Okay, so Autobuild has a couple options that you might want to distinguish between. you can run Autobuild in an option where it's rebuilding in place, and that basically keeps the connectivity, the residue names, residue numbers, all that sort of thing stays constant. And for rebuilding loops, that's probably a good way to run it if you wanted to do that. You can even specify what range of residues to work on. So you could run Autobuild and specify a chain name and a range of residues, and then it would just try to rebuild those as best it can. So that's one possibility for you. So yes, if you don't use that approach and you just let it rebuild everything, then you can lose your chain names and numbering system because it will try to rebuild everything and it'll try to reassign the sequence all over again. And so it might not give you the same answer. For the purpose of rebuilding loops, you might use a different approach though, which is just to use the fit loops tool. Basically, that gives you more control over working on a specific region. And actually the Autobuild, when it's doing fitting loops, it's more or less using this tool, but not quite as in a general way as you could do yourself. So I would recommend use fit loops, specify the beginning and end of the loop, and use that to try to rebuild a region. Now, Autobuild does have an additional feature that it's going to do things iteratively, and as you improve your loops, then you're going to improve the map, and then you can go through the whole process again. You can do that more or less by hand if you want, also by doing fit loops. And then after you do fit loops, you can run Autobuild, or you can run Autobuild in a mode that's just generating a new density modified map. Or you can just do refinement and calculate a map that way. That map might not be as good as the map from Autobuild. So back on your question of different maps, an initial map might be the map that was an experimental map that you came in with. Maybe that's a density modified map. After Autobuild, it will use any phase information that you supply. If you have experimental phase information like from MIR or from SAD phasing, it'll include that in the density modification process, trying to make a composite map that uses experimental information and density modification information and model information all together. And that map may be the most useful. It'll be a little bit different than your map that you just get from refinement, but it won't always be better, but in some cases it might be.
Great, thanks, Tom. So there are no, I don't see any new questions. Did anybody want to raise a hand to ask a question over the audio? Feel free to stick a hand up to ask your question. You can do that in the participant section. Remember, if you click the participants, you should have a raise hand button. Okay, I'm seeing.
So we actually, I think you might have missed one, Paul, from Jian Ying about zinc 2+ being mistaken for disulfide bridges.
Okay, yes, there was a question about strong difference density around a disulfide. Yeah, I think Dorothy pointed out radiation damage is one thing you should look at straight away in case the disulfide has been broken and you've basically got alternate conformations there. That does happen. Sometimes that's not so common, but occasionally you do see a genuine alternate conformation for a disulfide. At low resolution, I guess you could mistake a zinc for a disulfide, but at higher resolution, that wouldn't be the case. It would be very clear. So I think depending on your resolution, it could be something else. But I would look at the radiation damage idea first.
Okay. There's a chat and
well, there were a couple of hands that were up. Sorry, it's hard for me to see here. Mishba?
Hello, yeah. Can you hear me?
Yes, we can.
Yeah, okay. So I had a question about the situation where you have where you fit the ligand in the density, and then you see a part of it very clearly fit in the density, but a part of it you cannot see clearly, mostly because it's solvent exposed or it doesn't form good interactions with the protein backbone. So what to do in that case?
Well, Tom's smiling. Tom can say some things. I'm sure other people have things. Really,
Yeah.
Go ahead, Tom.
Michael. Sure. So bottom line is, in my opinion, if you see something clearly in the density, build it. If you cannot see something clearly in the density, don't build it, but tell people that it's there. And so in this case, that's what the ligand fitting tool will do for you. It'll build a part that's there and it'll leave off something that doesn't have any density for it. And if you had very high resolution data, then you might be able to model multiple conformations for such a situation. But if you don't have high resolution data, you don't know where that is. And so I say leave it off.
Yeah, what Tom said, I agree completely.
Also,
and sometimes,
because polder will help you with the solvent exposure.
Right, yes, if the solvent mask is sort of flattening out density, the polder map will be helpful. And you have to consider that sometimes when you don't see part of a ligand, it's because it really isn't there. Because what was put in the crystal maybe was not, or what actually crystallized with the protein is not what you thought it was, right? Because when the thing was synthesized, it was a mixture of things, and it was the smaller thing that actually crystallized.
And further to that, there's actually examples where the entity that the PDB has is actually really the parent, and when it binds with the protein, it loses half of the ligand, and you only have the active part of the ligand, and the rest is lost after the reaction. So yeah, it can be very different.
Right, but I think so. The idea of just modeling what you see and explaining is the best approach. You can put comments in your deposition to the PDB and in your paper, of course. In the future, this is one of the nice things about going to MMSIF. It will be possible in the future to mark atoms as being modeled, but not based on data, right? So in theory, then you could add a full ligand, but only mark half of it as being there because of the data. The other half is a model that you made up. So that is something that will be coming, but that's not available right now. And you need to think hard about whether a biologist looking at your structure is really going to interpret it correctly under those circumstances.
So can I quickly add one more thing to that? That if now, is there a possibility that if I change the occupancy of the ligand, that the density would change somehow after refinement?
If you set the occupancy to 0, then of course that part won't contribute. But yeah, you can of course refine the occupancy for the ligand as a refinable parameter, but that is really going to make the ligand occupancy match pretty much what you see in the map. So if you don't see half of the ligand, it's not going to magically appear because you refine an occupancy.
Yeah, you need to be clear about what density map you're talking about. So you said if you change the occupancy, whether it's going to affect the map. So what map you're talking about? You're talking about 2 Hopf minus of calc map, or you're talking about difference map. So yeah, I mean, both maps are going to change, and the Hopf minus of calc map is going to change to a less extent, I believe. But yes, definitely maps are going to change.
Okay.
Right.
Yeah, okay. Fine, thanks.
And there's a question from Eta. You're muted.
Oh, sorry about that. I had a question about after refinement. So like I have like, let's say an arginine that clearly is fitting into the density. It's like a 1.7 angstrom map. And then every time I refine it, it moves out of the density. and then I move it back, and I keep going back and forth. So part of the reason why I was asking you about that final refinement question, like, is there a way to just get it to stay put in the density instead of having Phenix Refine keep moving it around?
Yeah, I can respond that. So that shouldn't happen in the first place. And there've been versions of Phenix where there used to be a problem or bug related to this. So question number one, are you using the latest, the very latest Phenix version from Autobuild where this happens? So
I think it's the latest. I think the last time I updated it was, well, I downloaded it fresh in September.
So that's the 1.18 release probably.
yeah, I mean, my recommendation here would be really two things to do here. So try to go to Phenix web page and download the latest nightly build. There will be a release candidate released a few days ago, and try to do refinement using that release candidate. If the issue that you describe happens using that version, then that means there is something that we need to look at specifically. So in that case, please email me input model and data and tell what residue is misbehaving, and I'll take it from there right away and we'll do the best to address it. That should not happen. What you described should not happen in the first place. There's a problem and we need to address it.
Yeah, but you might want to, if you've got the real space refinement option turned on in Phenix Refine towards the end, it's likely that you might want to turn that off. I think, as Pavel says, it shouldn't make anything bad, but it's possible if you've got some distribution of density around a sidechain that real space fitting could potentially make a mistake. So that's one thing that you can do, is turn that option off, because at the end of refinement, it shouldn't be necessary to be doing that anyway.
Yeah, I call it lazy option, so you can do it. Yeah, but I'm really keen to make sure that never happens in the first place. So
right.
Thank you.
So we have a few more questions in the chat. I unfortunately have to go to another meeting, but if other people want to stay on and keep going, then that would be cool. I can pass this over to Nigel to be the.
Yeah, that's good. Thank you, Paul. There are 3 questions I see, so let's answer them. Luther talks about the squeeze procedure. I'm not very familiar with that, so does anybody have a comment on the use of the squeeze procedure, which we don't implement currently?
I have no idea what it is. So
Lothar, you should talk to us offline.
Oh, maybe you can explain it right now.
Oh yeah, put your hand up.
If you're still around.
You just talk to us, yeah.
Otherwise, if not, then yeah, send us an email to help list or specifically to somebody, and we'll try to look into it. But yeah, I have no idea what it is.
Yeah, thanks, Paul. Paul Ensley tells us it's a small molecule refinement technique. We should look at it anyway. The one question about ligand occupancy: if a region that indicates a bond between ligands shows 2FO minus F and red FO SC density, can that indicate a partial occupancy of that bond? Can a disappearance of the FO minus SC density at lower occupancy further indicate that? It looks to me like something that I would need to see, and that Pavel has an answer straight off the top of his head.
No, I don't really have anything specific. Region. No, I mean that's very specific. I guess we need to look at files specifically.
So Yosef talks about overfitting. He has at the end of his refinement, he has R factors of 15.5 and 18.4. He is.
Yeah, I think the key here is what's the delta. So you say increase, but you don't provide starting versus final numbers. So you provide final numbers. We don't know what's the increase. If you talk about delta being a fraction of 1%, then that's not significant. So we need to see the delta to judge whether that's significant and makes sense to look into.
Right. There's a question from Lucia.
So the starting R3, he says the R3 is 1898, and yeah, it's hard to tell still. I mean, I was hoping for small delta to be more definitive, but usually what you can do in this case, you can, well, it's a little bit tedious, but if you're really keen, you can, what it used to be called multi-start simulated annealing refinement, where you can run many refinement jobs, all starting with very similar models that are slightly perturbed to begin with, or you run simulated annealing on those jobs with different random seeds. Say do 100 jobs, 100 refinements, and then each of them will end up with different structures, very slightly different structure, having different R factors. And you plot the distribution of these R factors and see what's the significant delta that arises from the distribution of R factors from these refinements. So that's how we determine whether that difference is significant or not. Yeah, that's hard to tell still.
Okay, so there's a question about validating carbohydrates. I have just put a link in there for the quintessential place to do that. It's called PDB Care, and you can just Google PDB-Care, and that will send you to the place. It's the place where everybody starts any carbohydrate stuff, because those guys were the first to discover how badly the PDB was doing, etc. So PDB Redo, incidentally, does use the same place. So if you do it there, but this is the original place.
Okay, now I'm in a position to comment about squeeze procedure, as Paul and others point out what it really is. So yeah, if I understand correctly, so you basically can you got the difference map, positive density, and then you add that back to the structure factors. Yeah, that makes sense to improve phases. It's in a sense that's similar to R-FAR procedure, where you fill all the density blobs with dummy atoms. That may help to improve phases, and that looks interesting and appealing. My only concern is to what extent we can do it to not introduce model bias, or just back introduce errors into maps we look at. Yeah, I think that's the topic of separate research, in my opinion.
Okay, the next question relates to whether you should link ligands to zinc at 2 angstrom resolution. So in recent versions of Phenix, if your zinc is tetra coordinated to either cysteine or histidine, it automatically is taken care of. However, if you have water and you know, the ASP and the glues, etc., yes, I would recommend doing bond lengths and angles. Well, in my experience, I would start with bonds, put in the bonds so that you get the coordination sphere getting better and approximately what you want. And then you can add angles if necessary. But yeah, two angstrom is a good idea to have them. And there's some little tools that will help you with that are not completely exposed. So should contact me and I can help you with that quickly.